Okay, today we will just be reviewing for the exam, as David is excited about. And we will only have the university physics textbook they split one chapter. So for you guys, it's chapters 1 through 4. For the other students, it's chapters 1 through 3, just because the textbook splits. Hopefully by now the textbook situation is all sorted out, not getting confused about the two textbooks. Okay, so, whoops, can't do that because I forgot that I'm not using PowerPoint. So I pressed the button to advance in PowerPoint. You will have one question. The last question of the exam is a calculus-based question. And that question is going to deal with one or both of these two equations. So just to make sure it's clear so you don't get confused when you get there, what in the world? Anyway, sure, it's not a big deal. So you don't get confused when you get there. The last 5 questions, there's 5 questions in the synthesis section. The first 2 are ones, actually, the first 2 and the fourth one, you choose one of those 3. And then you have to do the third one and the last one. The last one, because it's the calculus-based one, you can't skip that one. The third one, because that's the one with doing the vector addition graphically. You can't skip that one, my goodness. I forgot to put in the graph for that. Things to do after class. It says on the provided graph, and I didn't put it in. But I will before the test time.
That'd be good.
Yeah. Otherwise, we get to the test and people are, I think my form is missing something. So you actually have 2 that you have to do, and then you just choose one of the remaining, I think it's 3. Whereas the other students, the physics 151 students, have one that they have to do, and then they choose 2 of the remaining 3 to them.
So I don't get it. Tell me what I do have to do, not what I don't have to do.
So you have to do the graphing one, the adding of the vectors on the graph, the calculus problem, which is the very last problem, and then you can choose one of the remaining 3.
Yes.
One of the what?
Remaining 3.
One of the remaining 3 what?
Problems in the synthesis section.
In the synthesis section. Okay.
Yeah.
You should have instructions.
So you have,
Okay, good.
because I have one locked in for them, and they have to do 2 of the following 3, and I have a second one locked in for you, then your last one is a choice from the remaining 3. Okay, so these 2 equations, I'm not going to reiterate what they mean. Instead, I'm just going to go to type of problems we could have. So we could have, for instance, given the acceleration, which I showed to the right, find the velocity and position as a function of time. Can you do that?
C is a constant, right?
C is a constant and B is a constant, yes.
Should be able to.
Okay, what about you, Oksana? Is that something you can do?
What's up?
If you're given this acceleration, can you find the speed and the time, or speed and position as a function of time?
No.
No. Okay, then I'll do it to make sure we can all do it.
Wait, are you just saying take the integral or do
Pretty much.
That's pretty much what it is.
Which one?
Of the top.
The one that's in a box here.
I know, but take an integral or derivative?
Well, that's the kind of decision that you have to be very clear on. Because no one's going to tell you take an integral or take a derivative. That's acceleration. And you know, by definition, acceleration is dv dt.
It's a derivative.
No. So an integral.
Okay.
Because it tells us to find either V or T. I think it was.
So since acceleration is dv dt, then I have dv dt.
Yes, I get it. So negative E. Yeah.
What do we call the step that I am just completing now?
Separation of terms.
Separation of variables. And in this case, it was very simple. It just involved multiplying across by dt. But as we saw in class, it's not always so simple. What is the key to separation of variables? I mean, it's in the words.
Separating stuff.
You need to have one variable on the left side, one variable on the right side, and you have to have your d's in the numerator position. Can't have them in the denominator, they need to be in the numerator. And so in this case, it's fairly easy. Now the left side only depends on velocity, the right side only depends on time.
So you're saying find, so what's the initial question? What's the,
How do we find the speed and the position as a function of time? And so we separated variables, and now we're integrating. So integral of the left side, that is very straightforward. Integral of dv is v. Put in our limits, and the left side is v
so
final
how do you
minus
get
v
rid of this
initial.
question?
Something like I have here.
So given AT, find VT.
And of course, it say find vt or find x of t. I wouldn't say or. Randy.
Got my lower late to class, but are we somehow reviewing this for the test?
Yes, we're just reviewing for the test. That's all we're doing. So the left side was simple. The right side, what's the integral of e to the minus vt?
Wasn't it negative BT times E negative BT?
That's what the derivative would have been.
Oh, you're right, you're right.
Plus 1.
No, it's just e to the negative BT.
You have to divide by the derivative of the exponent.
So negative BT e to the negative BT.
Well, divide by, so
Yeah,
it's,
wow.
you just said what you'd said the first time.
Right.
Okay, and then what about
Nope, never mind. Okay.
what about the integral of ct dt?
That's going to be CT squared over 2.
So putting in my limits, there's the upper and lower limits in the first term. There's the upper and lower limits of the second term. And of course-
we have minus 0 or not, do you?
No, I don't.
Okay.
And so, of course, most of us would write this in the simplest fashion. Yeah. Where now I've dropped off the final. And so there we have v as a function of v0. Let's add v0 to both sides. So I said v is a function of v0, v is a function of time. So there I have speed as a function of time. And then if I want to find position as a function of time, what would I have to do?
Change v to dx dt.
Right, change v to dx dt, rinse and repeat. So that's our first option.
I have a question.
Go ahead.
Okay, so if we wanted to look this up universally, what would we, I don't know, what would that be written as contextually?
Look up what universally.
These problems. So,
Like the argument?
so
Right, I have 5 problems written.
I know, but like, would you say find what?
Find v of t or find a of t.
So find velocity as a function of time, acceleration.
Yeah.
And I'll find something like that universally.
Yeah. Yes, David.
Are we going to work our way down the list, or can we kind of pick and choose?
You can pick and choose.
Number 4.
Given a, find a is a function of speed. Okay, that's why do you pick this one out? Because it's not as a function of time, it's a function of speed. Notice here we had v as a function of x, the same kind of complication.
Should you say dv?
Huh?
You'll just say dv?
What?
Instead of dt, you'll put dv?
No.
Oh.
No, because the definition of acceleration isn't changed. So jumping down to this one. So number 4, I'm just going to put here number 4. I'll put over here number 1. So we have, I wish my handwriting was,
That's number 5.
you're right. So what was the first step we did last time?
We changed DV, no, we changed
Yes.
whatever it was.
We did exactly what you said. We changed A to DVDT.
Okay.
And so that's the same thing I do here. I don't change the definitions of acceleration. And now what's the second step?
Separation of terms.
Separation of variables. And so, yeah, terms vary. There is a difference, but I assume you're on the right track. So we separate variables. So what I did before was I just multiplied both sides by dt. Why is that insufficient here?
Because we don't have any t's on the right side.
Well, we have a dt on the right side. We don't have any t's on the left side.
I mean, we can't integrate because there's nothing with respect to t in the right side of the equation. Like you need to have, instead of something like CV, have CT or something.
That's actually not the problem.
No.
The problem is the reverse of what you're saying. The left side. Well, actually, the variables aren't separated. They aren't separated because on the right side we have both v and t. We have to separate, so we only have v on one side and only t on the other. So we moved dt over so it's in the numerator position. That's what we've accomplished. dt is now in a numerator. But we haven't finished separating yet.
Right.
So how do I get my v over to the left side?
So you're going to have the equation 1 over v plus cv dt dv equals dt.
I hope you said this. I divide both sides by b plus cv.
Right.
Good.
And then I just said 1 over b plus cv times dv. So just kind of put my dv out to the side.
Would these be motion problems?
They are kinematic problems, yes. But in this case, you're using the calculus form of your definitions of velocity and acceleration, right? You're not using kinematic equations at all. This is how you derive kinematic equations. So now we have v's on the left side, t's on the right side, and once again, we can integrate. And so if I integrate this, I always use a u substitution here. There are plenty of people, my son is one, who's like, I can totally do this in my head. I don't need to use your silly u's. I might do that, but I also might make a mistake. So I use the u substitution. So it's not like I'm going to mark you wrong if you don't use a u substitution, as long as you do the integral right.
That's what we're hoping.
In essence, yes. But I have constants. That the reason I do the u substitution is so I get the constants right. So let u equal b plus cv. So du is equal to c dv. And you'll remember last time I screwed up at this point from last class period. That's what I forgot to do. dv is 1 over c du. I just replaced dv with du instead of forgetting the 1 over c part. And that's the whole reason of using the u substitution, so you don't make that mistake. So now my integral becomes...
Well, the constant's 1 over c. Right?
Yes, 1 over c u over.
And my u initial will be equal to, just plug in v initial, so my u final would be...
Why not just kind of skip that part of thing, the intervals, take the integral, back substitute back in, and then...
That's the way I always did it when I was in college. I'm just being explicit.
Okay.
Yeah, as long as you track it.
That seems like a lot of extra work to me.
Yeah, it's a lot more writing.
Right.
And as long as you track it, you're going to be fine. So I often write it without having limits at all. And then when I'm done, I say, okay, what was my lower and upper limit, and put it in at that point. But I want to make sure that I have it complete here so you don't look at it and say, hey, what happened to the limits? Why'd they reappear?
Okay.
So now if we do these integrals, the left-hand side now, this is the left-hand side, that's easy. T final minus T initial, which is 0. So I'm just going to put T final, especially because Dave's like, do we have to put that 0? No. Equals the right-hand side. Can't forget the 1 over C. Then, as Oksana said, natural log of U final over U initial. You know, just to save myself writing, I'm going to do the next step before I substitute. So how do I get rid of a natural log?
Everything basic.
Yeah, so smart move, multiply the C across, so those cancel, and then do E raised to this, E raised to that, and I have
You still need to keep the absolute values there or no?
as I said, I'm very loose with those. We physicists are sloppy about that. So my honest answer is I'm not sure. So I'd have U final is equal to U initial, E plus E to the, or times I was right the first time, E to the C T final, which of course would be crazy because what's happening with your U as time increases? It's blowing up, right? And since U is B plus CV, I have B plus CV is equal to B plus CV initial E to the CT. Or finally, V is equal to B over C plus V initial. That'd be my equation for the speed as a function of time. I don't think I made any mistakes. You're looking at me goofy, right? I had to subtract B from both sides, and I had to divide everything by C.
Oh, gotcha.
So now I have V as a function of time. What was I looking for?
You're looking for something.
Yeah, I don't remember. That was a long time ago.
That was a long time ago. I was looking for acceleration as a function of time, V as a function of time, and X as a function of time. So I found this one. So how do I go to acceleration as a function of time now? Yes. So now that I have this, life gets much easier. That was a much easier job, right?
What just happened?
I brought down the derivative of the exponent, which was C.
Right.
And so that's the line above the box. And then I just distributed that through. So B over C times C became B. And V naught times C became C V naught.
Okay, where's your, oh wait, that's a constant. Left.
Yeah, the B over C was a constant, so the derivative of the constant was 0.
Okay, why didn't you take the derivative of what's the difference?
Because those are all constants.
Okay, let's see what you did then.
Okay, so there we found the speed is a function of time, then the acceleration is a function of time, and how would you find the position as a function of time?
We take the integral of the v equation.
Yeah, take the integral of the V equation. So this is that A parenthesis T means as a function of time. This was V parenthesis T, this B is a function of time. So final step, What do I have to do first? Separation of variables. I'm going to erase the v equals so it makes it less cumbersome. Multiply both sides by dt. And it's completely separated. So then I have and I integrate each side separately. Left side is simple. X final minus x initial equals. The right side, we've already done this integral effectively. We did it in the first problem example. Integral of e to the ct is e to the ct divided by c. So I'm going to have and the integral of a constant. Got to put in our limits. When I put in those limits, remember e to the 0 is 1. So I'm going to have a total of 3 terms when I'm all done. So there I did the e to the ct limit is what's in the brackets.
Why do you have to subtract the 1?
Because e to the 0 is 1. This is,
Oh, you just really condensed everything down.
that's e to the 0 is what gave me the 1.
So you just kind of, because the way I'd always been taught is you start with the whole equation and put top variable and then do the subtraction of everything else.
Yes. You can do it term by term, or you can do the whole thing. No one's going to care one way or the other as long as you have a method and you don't mess up. So I do it both ways depending on what I have. So in this case, the first term is easy to do with the 2 limits, and then the second term is easy to do with 2 limits. So I did that. Sometimes I do exactly what we do. And so, I mean, at this point, I could drop the 0, change my t finals to t's, but we're done.
Yeah.
So now this problem, since David jumped us to the end, we pretty much have covered all the skills, right? Because we had to integrate with this one, we had to differentiate with this one, we had to change the variable with this one. If you could do all of the different steps that we just did, you're set for the problem.
Are we going to have to do anything funky with integration, like
You won't have to do integration by parts or something like that. That's what you do.
yeah, that's what I mean. Like,
Yeah.
because
The integrals that you have, and I'll be very straightforward. Integrals are derivatives, I should say. The integrals and derivatives you have are sine, cosine, exponential, or polynomial. Can you all do derivatives and integrals of that set?
sine, cosine, and polynomials.
Hmm?
Sine, cosine, and polynomials. That's what you said.
And exponential.
And exponential.
So polynomials would be
That's like integral of x cubed or derivative of x.
Right.
Well,
Will we have a special cheat sheet for the integrals?
You won't, because I expect you to know how to use those, right? I chose ones that were simple integrals, so you wouldn't need to cheat sheet on the calculus.
Just to over-
has this.
review again.
Yeah.
You said, so you go from acceleration to velocity. That's innovation.
To go from acceleration to velocity is going to be integration, right? Because a is dt.
And then velocity, acceleration, velocity,
Derivative.
derivative, obviously the opposite. Then from velocity to speed, is that derivative?
Well, velocity speed would be after the acceleration you drop the direction, not what you meant.
Is that all we have to know?
You meant probably from velocity to position, right?
Position, that's the other.
Yeah. And so velocity position, you're integrating if you're going toward position. So acceleration, velocity, integration, velocity to position, integration.
Acceleration, velocity.
You're differentiating through going toward acceleration. So X to B, B to A, those are differentiation. And that goes back to just the definition of what acceleration is, the definition of what velocity is.
Okay, so just to review, the integral of sine is cosine. No.
Okay, so there is a sign thing to worry about. And the way I remember it, it's probably the dumb way, but it's the way I do it. I know that sine at time equals 0 has a positive slope.
Yes.
So that means the derivative of sine is positive cosine. Right?
Okay, yeah, that makes sense.
And so if we reverse that, that means the integral of cosine has to be positive sine.
So then the integral of
Sine
sine
is
is
negative
negative
cosine.
cosine.
Yeah. That's how I remember it.
I'll just have to do my best.
I always go back to the very beginning of what a graph of sine looks like, no matter what I'm doing, integrating or differentiating the sine and cosine, I always go back to that. It's not a touch step.
So it's the whole slope being positive, and so if the sine slope is positive, then the integral has to be positive.
No,
Or the derivative has to be positive, which would be positive cosine. Okay, that makes sense.
And it's switched, so if the derivative is positive, then the integral is going to be negative.
Okay, question on 4 here. You went from AV
Yes.
to VT.
Right, because that's the only way you can go. You can't go directly from A to AT.
Oh, no, I'm not curious about that. My question is, why did your V variable change to T?
Okay, so definition of A is dV dt.
Right.
And so I have A as a function of V. So I have a function of V is equal to dV dt. What are the two variables? Because that's what my answer is going to be.
Right.
It's going to be between V and T. So I can do V as a function of T, the standard, or I can do T as a function of V, which would be really bizarre.
Use a function of time and function of velocity.
Right, that's just inverting the process, which may or may not be possible. That's once you've done your calculus, just solving for the variable.
So separate variables, integrate, set your bounds. Or going from like position to velocity, velocity, acceleration.
Going from, going from acceleration to velocity, velocity to position.
That's the integration.
I guess what I'm confused about is how can A of T be dV dt and A of V also be dV and dt?
Well, the definition of A is dV dt.
Right.
And so it's that relationship that I started with.
Okay, so we only care about the letter or variable outside the parentheses.
Well, because I had A parentheses B, then when I did A is equal to dV dt, I had a function of V is equal to dV dt. Whereas in the first one, I had a function of T is equal to dV dt. So the fundamental difference was I had one was a function of V, so I had to divide everything by that function of V to get on the same side as V. That's dV. The other one I had a function of T, I just left it there and then applied the dt across.
Okay, so then for number 5, what we would do is we would integrate to get x of t.
Yeah, because dV is dx dt.
Right,
So you
but
can integrate
we'd
it.
have to do the whole
That was
dv over the, or in this case, the dx over d plus cx equals dv.
We have dV is equal to parentheses b plus cx dt. And then we have to divide everything by b plus cx. So we have dx over b plus cx equals dt. Which is exactly the same as what we had in our last integral, only the names have been changed. And so then the integral is exactly what we just did, except for we now have x is a function of time, and then take the derivative to find b is a function of time, take another derivative, find the function of time.
That's confusing to me, the whole, wow, it is a function of something.
So it's that, what I circled.
So really that's what he was saying, like you wrote. What were you saying?
I was just confused on like how the function of time and function of x and things like that. How do you see that? So for everyone, it says given acceleration as a function of time when accelerated.
Okay, so, take this with me,
Yeah.
because I will not forget it.
Is that x and y coordinates and stuff?
So, for just how to approach it. I think that's what we're really zeroing in on. So if I'm asked to find, or excuse me, not if I'm find, if I'm given v is a function of x. Yeah. I don't care right now that this is x. What I do care is that v is equal to dx dt. That's what I care about. So since v is dx dt, I make that substitution, and now I'm going to have some function of x is equal to dx dt. And then I do my separation of variables. If this had been v is a function of t, I still would have done the same thing. But now I would have had a function of t on the right side, so separation of variables would have gone differently.
It wouldn't be dx or dt, dt, something like that. Just
No.
dx, dt.
Yeah, it's if it's v, it's dx dt. No matter how you slice and dice it.
V is dx, dt.
A
Yeah.
is DV.
And a is dv dt. Regardless of what the variable is. The variable is going to affect how I separate variables after I do that first step.
Okay, that kind of makes sense.
Yeah.
So that's why in my first slide here, it's going to have one of those two equations. If it's v equals this, you know you're going to say, that's dx dt equals this. It says a equals this, you're that's dv dt equals this. And then you do your work from there.
Oh my god. Okay, cool.
Okay,
I understand that. And I did my thing wrong.
and you did your thing wrong.
Yes, because I did dv dx or dx dv instead of dx dt.
So you have v.
I just want to know one thing.
I'm not sure what you were wanting to look at actually. So I don't know.
I was wanting you to look at this certain bit.
Oh, yeah.
Then instead of dv, this should be dt. Because v of x is.
So no, that's correct. Except for
I use dv instead of dt.
oh, wait.
So I did v of x. V of
What's
dx.
your
Oh, it should be
pin?
dx to t.
And then personally, I understand that this is outside and that I don't do
You must, otherwise it's mathematical nonsense.
Through
We can't have mathematical nonsense.
I can, because if I understand it, it's fine.
That's the way I felt in college too. I was disabused of that with some low score in graduate school.
I have a question with this thing.
Okay, nomenclature.
Nomenclature.
Nomenclature, that means names. It's just a word that means names. It's not some special physics.
Is it, can I look it up and it's universal so I can like research it myself?
Well, nomenclature just means names.
Yeah.
No.
You'll find it in all kinds of different contexts.
Okay. Okay,
What
so
are those representations?
So,
I just want to know what X would equal and B would equal and A would equal. I feel like that will break it down to the lowest form to conceptual level. So X, or would that be X prime? Is that what you're doing?
Right, good.
Oh, I didn't really know. Maybe a different perspective.
So basically, that's just the derivative of the variable.
if you use a dot in physics, a dot over a character means you're taking a derivative with respect to time. So it's just a very quick way of writing a derivative with respect to time, to put a dot over it.
So why don't we just say prime?
Because prime is different in physics.
Of course it is.
But that's not really a question. I want to know.
Prime means with respect to position. So x prime is 1. Right, dx is 1.
Okay, so the dot is with respect to time, prime is with respect to position.
Right.
Okay.
And of course,
Taking the derivative of it.
they both mean take a derivative, but got to say what it's respect to.
Right.
And the whole goal is to make it quicker. So in advanced classes, that's how we write our math. We just do x dot, because it's many times shorter than dxdt.
Okay, so instead of all that you wrote, my question is like x dot, that is derivative of x, right?
With respect to time.
Which is distance, the derivative of distance.
Derivative of the position.
Yes, and then v dot, that's the derivative of velocity. Okay,
With respect to
so,
time. Right, the dot indicates with respect to
it's-
time, not just the derivative.
you don't have to say time, right?
Well, you do.
Yeah.
That's the whole point of the dot.
Okay,
Velocity
so,
with respect to something else.
Yeah, you can do the derivative of velocity with respect to position. You can have v prime.
okay, so like if it's not respect to time, what would it be?
Well, like we said, you can have a prime. I just said you can have v prime. That's v dx.
Oh,
But the dot is specific.
Specific.
Yes. And that was the whole point. Which is why you can't just say derivative of this. You have to say with respect to time.
okay, so, I don't know, could we just write it like that instead of doing?
Yeah, I taught you that so you can read books and not be like, I don't understand this. It's all, I don't think our textbook uses the dots. I know I'm not using the dots in class, but it's still something, right? So it's not going to be on the test, but it's still something to know. So when you see it written down, you're not like, okay, now they just punted me to a different thing that we never covered.
No, I mean, I prefer to see it with the dots, because like all the divisions,
Because it's short.
I mean, it is short, but
you know.
for the level of stuff we're doing, if you're saying this for the upper level stuff. just-
Well, it's when you're doing a whole lot of derivatives,
Right,
you save a whole lot of time. Just like, we have other things, Newton summations, implied summations, and things like that. If you don't know, you look at it, it's a completely different equation than you thought it was, because you don't know the nomenclature.
Okay, so the exam's at 2 today, right?
And true today, yes.
Okay, good, because I didn't do my lab quiz.
Yeah, there's no lab quiz because there's no lab. Okay, that's what I got. Any other questions? I mean, you can ask anything.
I just want to reiterate again. So how we solve these is separate variables,
Mhm.
we integrate,
Or
Derive.
or derive.
if you're going from acceleration or velocity toward position,
Yes, that's derivative.
then you make the substitution, separate variables, and integrate.
So use substitution over time.
Well, the substitution of, depending on which problem, you kind of probably doing A equals D dt or V equals dx. That's what I meant by substitution.
Okay. That makes sense. So A, B, E, going that direction, integrals. E, B, A, derivatives.
Right.
You set your bounds, of course, variables, and then
do math.
Do math, yes, okay.
Lots of it.
Lots of different variables. That confuses me, variable math. I like numbers.
Yes. Numbers are fun.
I was gonna say you'll get used to it, like, as an engineer, you're probably always gonna be much more than numbers.
Yes.
As for me, well,
Who knows what David's going to be into? Fast cars.
I could be in fast cars.
You're gonna be a science teacher like your pops? Is that your plan?
Yeah, except at the college level.
Ah.
So, chemistry
I
specifically.
just want to
Not
cry.
this.
Well, you'll make plenty of friends. It just won't be me.
Uh,
Unless you choose to follow Ken and be a physical chemist. Then we can still be friends.
I mean, I prefer the physical aspect of chemistry versus the biological aspect.
Well, let me stop the recording. I've already